In this video, we will see problems on reducibility of polynomials, and most of the problems was asked in the NET examination. So let us start with the first problem. For what value of n the polynomial px is equal to 1 plus x square and so on up to x raised to n is irreducible over q. So they are asking which of the following polynomial is irreducible over q. First of all, now options are n equal to 10, 21, 30 or 40. So let us see for n is equal to 10 what we have. N is equal to 10, then it gives me px is equal to 1 plus x square plus and so on x raised to 10. But this is what? It is 511x. The 11th cyclotomic polynomial, and we have a result about cyclotomic polynomial. So let me state the result. 5px is what it is, x raised to p minus 1 plus x raised to p minus 2 plus and so on x plus 1 is irreducible over q for all prime p. So here 11 is prime, here 11 is prime, so this one is what? Irreducible over q. So for n equal to 10, the given polynomial is irreducible over q. So first option is correct. Now similarly for n is equal to 30. So let us go for n is equal to 30. It is what? Px is equal to 1 plus x square plus and so on x raised to 30, and that is what? 531x. See, the definition of 5px is, if here 5p, then it start with x raised to p minus 1, and if x raised to p minus 1 is highest degree, p minus 1 is the degree, then it is p minus 1. Here 30 is the degree, so it is next 31, and 31 is prime. So this one is what? It is irreducible over q. So 30 is also correct answer. Now let us go for n is equal to 40. It is px is equal to 1 plus x square plus and so on x raised to 40, then it is 541x, and again 41 is prime, so it is irreducible over q. So 40 is also correct answer. Now let us go for n is equal to 21. So n is equal to 21. Implies px will be what? 1 plus x square plus and so on x raised to 21. So if I write in the phi notation, then it will be 522x, but 22 is not prime. See here 22, this one is not prime. So I can't use the result 5px is irreducible because p is not prime here. So but in this case let us write px is what 1 plus x square plus x cube plus x raised to 4 plus x raised to 5 plus and so on. It will be x raised to 20 plus x raised to 21. So in this polynomial there are total 22 terms. See, x to x raised to 21 there are 21 and 1 is 22th. So there are 22 terms. So if I pair the terms like 1 plus x plus from these two terms I take x square is common, then it is 1 plus x plus similarly here x raised to 4 is common, then 1 plus x and so on, and last two terms x raised to 20 common, then it is 1 plus x. So I can write it is 1 plus x into 1 plus x square plus x raised to 4 and so on x raised to 20. So here px, this is also px, so therefore px is reducible over q. It is not irreducible, it is reducible. So option B is not correct. So option B is wrong. Now problem number 2. Let A is equal to n belongs to n such that there exists px belongs to rx such that degree of px is equal to n and px is irreducible over r. So we have a set A. Then the set A is what? It is countably infinite. Option B finite, singleton or uncountable. So here what is the set exactly? Here A is what? A is a set and it contains n belongs to n such that for n there exists polynomial in Rx with degree n and it is irreducible over R. So we are collecting in set this set A is a first of all it is a subset of n and n is what? N is the degree of polynomial over Rx and it is irreducible. If you have a positive integer n so that the degree of a polynomial is n and it is irreducible over R, then that n is a member of set A. So and we are collecting n from natural number. So let us start with n is equal to 1, whether n is equal to 1 is element of A or not. So let n equal to 1, then I have you take px is equal to say 2x plus 3, then degree of px will be what? It is 1 and px is irreducible over R. So therefore 1 belongs to A. Not only 2x plus 3, but you may take ax plus b, where a is not equal to 0 and ab belongs to R. You may consider any polynomial of degree 1, then it will be irreducible over R. So for n equal to 1 we have a polynomial over R which is irreducible. So degree of px is 1 and it is element of A. Now n is equal to 2. You consider px is equal to say x square plus 1. Then it is a polynomial over R. Degree of px is 2, and px is irreducible over R, because roots of px are plus or minus I, so it is irreducible over R. So by definition of A, 2 belongs to A. Now for n greater than or equal to 3, let me consider. So if px is a polynomial of degree n, so let n is greater than equal to 3, and let me write in this way. Let px is equal to an x raised to n plus an minus 1 x raised to n minus 1, so on, a1 x plus a0 belongs to Rx. Then degree of px is equal to say n, where an is not equal to 0 and n is greater than equal to 3, implies px is reducible over R. We know any polynomial of degree greater than or equal to 3 over R is always reducible. We know this result. So there does not exist any polynomial of degree 3 greater than or equal to 3 and which is irreducible over R. So by definition, n will not be in A for all n greater than or equal to 3. So therefore A is what? A contains 1, 2, only these two elements. So therefore A is a finite set. So if you see the options, then it is not countably infinite, it is a finite set, it is not a singleton because it contains two elements 1 and 2, and it is not uncountable. So option B is correct. Now problem number 3. The problem was asked in NET December 2019, part C, which is of 4.75 marks. Problem says that let fx belongs to zx be a monic polynomial of degree n. So here the word is what? Monic polynomial of degree n. Then which of the following are true? If fx is irreducible in zx, then it is irreducible in qx. If fx is irreducible in qx, then is irreducible in zx. If fx is reducible in zx, then it has a real root, and if fx has a real root, then it is reducible over z, that is reducible in zx. So before going the solution of the problem, let me recall the definition of monic polynomial and a result regarding that. So let me clear the definition of monic polynomial. A polynomial fx belongs to Rx is called monic polynomial. if coefficient of leading term or leading coefficient, if let me write leading coefficient, if leading coefficient is 1 is what? Unity of ring R, then polynomial is called monic polynomial. And we have a result, another result, first one, if fx, let fx belongs to zx, if fx is reducible over q, implies fx is reducible over z. This is the result. But the second result is says that if fx is monic, fx belongs to zx is already we have taken, but if we give one more condition on fx, that is if fx is monic polynomial, then see in first result, if fx is reducible over q, implies fx is reducible over z, but the converse is not true. Here converse is not true. But if I consider fx is a monic polynomial, then we have this result, fx is reducible over q, implies fx is reducible over z, and the converse is also true. So we have if and only if result, if fx is monic polynomial. So if I rewrite this result in another way, that is the contrapositive of this result is what? Fx is not reducible over z, that is fx is irreducible over z, then fx is not reducible over q, that is fx is irreducible over q, and both the way. So another way of writing this result is fx is irreducible over q if and only if fx is irreducible over z. So that is, in short, if fx belongs to zx is monic, then reducibility over z is same as reducibility over q in some sense. So concept of reducibility and irreducibility are same over z and q if fx belongs to zx and it is monic. So I request try to understand this result properly, because we will frequently use this result that fx is monic polynomial, then reducibility and irreducibility are same on z and q throughout the lecture. So now let us go for the options. Then first option says that if here fx belongs to zx is monic polynomial and fx is irreducible in zx, then it is irreducible over qx. So answer is this option is correct. Why? Because due to this result, irreducibility and reducibility are same over z and q. Now second option says that if fx is irreducible over qx, then it is irreducible in zx. So that is also correct, because fx is monic polynomial over z. Now see, if fx is reducible in zx, then it has a real root. So fx is reducible in zx, then it claims that it has a real root. So for that let us see. So for option C, let me, you take fx is equal to x raised to 4 plus 2x square plus 1. Then this is what it is, belongs to zx and it is monic. But it is what? It is x square plus 1 whole square. That is it is x square plus 1 into x square plus 1. So fx is what? Reducible over zx, reducible over z. So fx is reducible, it is monic, but then option C says that it has a real root. But the roots of fx are what? Roots of fx are x is equal to plus I or minus I. These are the only roots, plus or minus I. So these are not real. Roots are not real. And in option C, they claim that if fx is reducible in zx, then it has a real root. Here we have fx in zx, which is monic, and it is reducible, but it has no real root. So option C is wrong. Now what about option D? If fx has a real root, then it is reducible in zx. See, let us see. For option D, you take gx is equal to x square minus 2. Then it is in zx, it is also monic, and roots of gx are plus or minus under root 2. So these are real. These are real. So all the hypotheses are satisfied. Then it is reducible in zx. But gx is equal to x square minus 2 is not reducible in zx. So option D is wrong. So option A and B are correct. Now problem number 4. For which of the following primes p does the polynomial x raised to 4 plus x plus 6 have a root of multiplicity greater than 1 over a field of characteristic p? So before going this definition, before going this problem, let me recall one result. Let fx be a polynomial over f, where f is a field. Then alpha belongs to f is a 0 of fx of multiplicity k if and only if its nth derivatives at alpha are 0, where n is equal to 0, 1, 2 up to n minus 0, 1, 2 up to k. And k plus 1th derivative of alpha is not equal to 0. Then we say that then we have alpha is a 0 of multiplicity k. This is a result. And here what do you mean by f0 alpha? So here let me here f0 alpha is nothing but 0th derivative means value of the function at alpha. 0th derivative at alpha means we mean this. So this result says that if a root has multiplicity k, then its first k derivative will be 0 and value of the function at alpha is also 0, and k plus 1th derivative is non-zero. So here my polynomial is what? So here you take fx is equal to, let fx is equal to x raised to 4 plus x plus 6, and for field of characteristic p, and field of characteristic p is what? Field of characteristic p is what? It is only the field is zp. So you consider fx belongs to zpx, where p is prime. Then characteristic of zp is p. So now let us consider its derivative. So f dash x will be what? 4x cube plus 1. So again it is over zpx. So now let us consider case 1. P is equal to 2. So for p equal to 2, our fx is equal to this x raised to 4 plus x plus 6. It is belongs to z2x. You look at the polynomial in z2x, and its derivative f dash is 4x cube plus 1. It is also in z2x, right? And z2 is what? 0, 1. Now first of all let us see whether this polynomial over z2 has a 0 in z2 or not. If it has a 0, then we will see what is the multiplicity of that 0. So let me consider f of 0. So f of 0 will be what? 0 plus 0 plus 6, but it is what? 6, and 6 is 0 in z2. But what is f dash 0? So f dash 0 will be 4 into 0 plus 1, that is 1, which is not equal to 0. So therefore multiplicity of 0 is equal to 1 only, which is not greater than 1, which is not greater than 1. And what about f of 1? So f of 1 will be 1 plus 1 plus 6, it is 8, it is 0. But f dash 1 will be what? It is 4 into 1 cube, it is 1 plus 1, so that is 5, and 5 is 1, which is also not equal to 0. So multiplicity of 1 is also 1, which is not greater than 1. So for p equal to 2, so here we say that zeros of fx in Z2 are both 0 and 1, but they have multiplicity 1, and we are seeking for the prime for which the multiplicity of a root of this polynomial has greater than 1. At least one root has multiplicity greater than 1. Here both the root 0 and 1 has multiplicity 1. So P is not correct option. So option A is wrong. Now let us go for P equal to 3. So for case 2, P equal to 3. So our fx is equal to x raised to 4 plus x plus 6. Belongs to Z3 x, and f dash x will be what? 4x cube plus 1 belongs to Z3 x. But in Z3 6 is 0, so it is what? X raised to 4 plus x only, and f dash x will be what? This will be x cube plus 1, because 4 is 1. So and in Z3 we have 3 members 0, 1 and 2. So now if you consider f of 0, then it is 1 plus it is 0 plus 0, it is 0, but f dash 0 will be 1, which is not equal to 0. So it gives me what? Multiplicity of 0 is equal to 1. Now f of 1 will be 1 plus 1, which is equal to 2, which is not equal to 0. So 1 is not a 0, so there is no no meaning to talk about the multiplicity of 1. So means what? 1 is not a 0 of fx. Now you look at 2, so f of 2 will be 2 raised to 4 plus 2, it is 18, and 18 is 0, and f dash 2 is what? F dash 2 is 2 cube plus 1, that is 9, so that is also 0. So now we have to go for f double dash. So f double dash will be what? F double dash x will be 3x square plus 3x square. So f double dash 2 will be 3 into 2 square, so it is also 12. and 12 is also 0. Now you go for f triple dash, and f triple dash is what? It is equal to 6x. So it is 6 into 2. So it is also 12, and it is 0. And similarly f fourth derivative at 2. So okay, whatever the fourth derivative or third derivative, but from here, so let us find it is fourth derivative at x will be 6, and 6 means 0. So it is 0. So from here we can say multiplicity of 2 is greater than or equal to 2. Its multiplicity is greater than or equal to 2. So we have a 0 of polynomial over Z3, so that its multiplicity is greater than 1. So it is strictly greater than 1 also. So option B is correct. For p equal to 3, we get a 0 of given polynomial whose multiplicity is greater than 1. Now if you find similarly you try for yourself for p equal to 5 and p equal to 7. There does not exist any 0 of fx having multiplicity greater than 1. So option C and D are not correct. Now problem number 5. Fx is equal to x cube plus 2x square plus 1, and gx is equal to 2x square plus x plus 2. Then over Z3, fx and gx are irreducible. Fx is irreducible but gx is not, and gx is irreducible but fx is not, and neither fx nor gx irreducible. So they are asking about the reducibility of fx and gx over Z3. And here you observe the degree of fx and gx are 3 and 2 respectively. And we have a result. Let me recall the result. Let fx belongs to fx, where f is a field. Let degree of fx is equal to 2 or 3. Then fx is reducible over f if and only if fx has a 0 in f. So the problem of reducibility is equivalent to it has a 0 in f or not. But for that our degree of the polynomial should be 2 or 3, and here the degree of the polynomial of fx is 3 and degree of polynomial of gx is 2, and over z3, and z3 is a field, so we can use this result. So to check whether fx is reducible or not, we have to just find whether fx has a 0 in z3 or not. Similarly, gx has a 0 in z3 or not. So let us go for fx. Fx is equal to x3 plus 2x square plus 1. It is over z3x. So here degree of fx is equal to 3, and z3 is filled. 3 is a field, and it contains 0, 1 and 2. So f of 0 will be what? 0 plus 1, which is equal to 1, not equal to 0. F of 1 will be 1 plus 2 plus 1, it is 4. 4 it is equal to 1 in z3, which is not equal to 0, and f of 2 will be 8 plus 4 plus 1, it is 13, and 2 cube. 2 cube is 8, and again this will be also 8, it is 17, and 17 in z3 is a 2, which is also not equal to 0. So this gives me what? Fx has no 0 in z3, so it gives me fx is irreducible over z3. Now gx is 2x square plus x plus 2 over z3x, and degree of gx is equal to 2. So g of 0 and g of 0 will be 2, which is not equal to 0. G of 1 will be 2 plus 1 plus 2, which is 5, and it is 2 in z3, so it is also not equal to 0. And g of 2, it is g of 2, it is 2 into 2 square plus 2 plus 2, so it is 12, and 12 is 0. So it means what? Gx has a 0 in z3, so therefore gx is reducible over z3. So gx is reducible and fx is irreducible. So options, if we look at options, then gx, first option fx and gx are irreducible, so it is not correct. Second option says that fx is irreducible but gx is not, so that is correct. Option B is correct. Option C is gx is irreducible but fx is not, so that is wrong, because gx is reducible and neither fx nor gx is irreducible, so that is also wrong. So option B is correct. Now Problem number 6. Let n belongs to z, then which of the following are correct? So here we have given n is integer, and they ask polynomial x cube plus nx plus 1 is irreducible over z for every n. B option. The same polynomial x cube plus nx plus 1 is reducible over z if n is 0 or minus 2. And the polynomial is irreducible over z if n is other than 0 or minus 2. And x cube plus nx plus 1 is reducible over z for infinitely many n. So here let me say first of all, let fx is equal to x cube plus nx plus 1. Now for n equal to 0, so see, you consider for n is equal to 0, f of x will be what? It is x cube plus 1. But x cube plus 1 is what? X plus 1 into x square minus x plus 1. So it means what? Fx is reducible, because fx is what? Product of two polynomials over zx, and none of them is unit. So fx is reducible over z. So option A says that x cube plus nx plus 1 is irreducible over z for every n. No, for n equal to 0 we have fx is reducible. So option A is wrong. So now let us go for option 2b. The same polynomial is reducible over z if n equal to n belongs to 0 minus 2, means n equal to 0 or n is equal to minus 2. So for n equal to 0 already we have proved that fx is reducible over z. So now let us go for n is equal to minus 2. So let us check it. For n is equal to minus 2, so let us see what happened for n is equal to minus 2. So fx is what? X cube minus 2x plus 1. So by inspection, if you consider f of 1, then it is what? F of 1, then it is 1 minus 2 plus 1, so it is 0. So it means what? Fx as a 0, alpha is equal to 1 in z. So it has a 0. So can we say that it is reducible over z? We have a result. If fx has a 0 in f, then x minus f is a factor. X minus alpha is a factor if alpha is 0. But here z is not filled. So let us manually verify whether x minus alpha is a factor or not. So you divide this, you consider x cube minus 2x plus 1, and you divide it by x minus 1, because 1 is a 0. So here we have x square. So it is x cube minus x square minus plus. So it is x square minus 2x plus 1. So again here we have plus x. So x square minus x minus plus, and we left with minus x plus 1, and here we have minus 1, and here we have minus x plus 1 plus minus, so we have 0. So therefore x cube minus 2x plus 1 is what? X square plus x minus 1 into x minus 1. So therefore this is what? It is reducible in zx. It is reducible in zx. So for n is equal to minus 2 it is reducible. For n equal to 0 fx is also reducible. So option B is correct. Option B is correct. Now option C says that x cube plus nx plus 1 is irreducible over z if n is not 0 or minus 2. So if you take n is the value other than 0 and minus 2, then it is irreducible. And in option B already we have seen it is reducible for 0 and minus 2. So in option C it is irreducible for every n if it is different from 0 and minus 2. So let us see. So before going that you observe that for, let me see, for option C, for that let n belongs to z and n is not equal to 0, n is not equal to minus 2, first thing. Now you observe that fx is equal to x cube plus nx plus 1, this is monic polynomial of degree 3, and we may consider it is over q. It is over z, but it is at same time it is over q also. So it is monic polynomial over zx or in zx, and I want to check its irreducibility over z, but it is monic, so it is equivalent to check its irreducibility over q. So let me first of all it is consider in qx. So now suppose fx is reducible over q. Reducible over q. Since degree of fx is equal to 3 implies, and q is a field, and q is a field, so implies fx has a 0, say alpha in q. See, we know that if a polynomial has degree 2 or 3 and polynomial is over a field f, then it is reducible if and only if it has a 0. So here degree of fx is 3, q is a field, and it is reducible, so it must have a 0. So let me say that 0 is alpha. So let alpha is equal to r by s, where GCD of r and s is equal to 1. So by rational root theorem, by rational root theorem, this r numerator will divide the constant term, and here constant term is 1. So let me write here, by theorem r will divide the constant term, it is 1, and s will divide the coefficient of leading term, that is also 1. So it gives me what? It gives the value of r and s. R is what? It is plus or minus 1, and s is also plus or minus 1. So it gives me what? R by s. If I consider R by s, then 1 upon 1, 1 upon minus 1, 1 upon 1, 1 upon minus 1, minus 1 upon 1, and minus 1 upon minus 1. So all four combinations are possible, and it gives me 1 or minus 1. So if fx is reducible over q, then the possible value of alpha, it means alpha is equal to 1 or minus 1, and alpha is what? Alpha is a 0. Alpha is a what? Alpha is 0. So therefore f of alpha equal to 0 implies alpha must be 1 or minus 1. So let us check manually for alpha equal to 1 or minus 1. So here I need some more space, so let me add one more page. So here alpha is equal to 1 or minus 1. So let us check manually. Now f of 1 will be what? It is 1 cube. Fx is x cube plus nx plus 1. So let me write now fx is equal to x cube plus nx plus 1. So f of 1 will be 1 plus n plus 1, that is n plus 2, which is not equal to 0 because n is not equal to minus 2, and f of minus 1 will be minus 1 minus n plus 1. So this is equal to minus n, which is not equal to 0 because n is not equal to 0, because we have considered n is other than 0 and minus 2. So therefore if by rational root theorem, if fx has a rational root, if fx has a root alpha, then alpha must be what? 1 or minus 1, and by manually checking, f1 and f minus 1 are non-zero. So therefore fx has no 0 in q. So therefore fx is irreducible in q, and fx is also monic. So therefore fx is irreducible over z if n is not equal to 0 and minus 2. And let me recall once again, here I am using the fact that fx is irreducible over q and fx is monic. So the reducibility and irreducibility will coincide over z and q whenever fx is monic polynomial, and we have studied the result. Let me show you that result in problem number 3. So you just go through this result once again. So this is a result, and which I am using here also. Therefore fx is irreducible over z. So finally what I get, if n is not equal to 0 and minus 2, then it is irreducible over z. So this option C is correct. So we have proved in option B z is reducible only for 0 and minus 2, and it is irreducible for 0 and minus 2. So ultimately in account it is reducible only for 0 and minus 2. So it is reducible over z only for finitely many value, and here they in option D they say it is reducible over z for infinitely many n. So that is wrong. So option D is incorrect. Now problem number 7. Problem 7 says that it was asked in December 2018, 4.75 marks, C part. Fx is equal to x raised to 7 minus 105x plus 12. Then which of the following are correct? Fx is reducible over q. There exists an integer m such that fm is 105. There exists an integer m such that fm is 2. And fm is not a prime number for any integer m. So first observation, here fx is equal to x raised to 7 minus 105x plus 12. It is over zx, or you may say it is over q. Okay, it belongs to zx, and fx is monic. One thing, it is monic polynomial. So first option says that fx is irreducible over q. So clearly this is what here 3 divides 12, 3 divides minus 105, and 3 does not divide 1, and here 12 is constant term, minus 105 is coefficient of x, and 1 is a leading coefficient, and 3 square does not divide 12. So therefore fx is 3 Eisenstein. So therefore fx is irreducible over q. So therefore option A is correct. Now it says that option B, there exists an integer m such that fm is 105. So value of the polynomial at some integer is 105, they claim in option B. So for option B, so here we prove that option A is correct. Now let us go for option B. So for that, let you take m belongs to z, then m may be even or m may be odd. So if m is even, then m is equal to of the form 2k, and it is odd, then it is of the form 2k plus 1. So case 1, m is equal to 2k, then f of m is equal to f of 2k, and f of x is what? F of x is x raised to 7 minus 105x plus 12. So it is 2k raised to 7 minus 105 2k plus 12. So now k may be odd or even, but 2k is always even. So 2k raised to 7 is also means 2k is odd number, 2k is even number. Now even number into even number into even number 7 times, so it gives me even number. But k is positive or negative, so 2k may be positive, negative. K is positive, then 2k raised to 7 is positive. K is negative, then 2k raised to 7 is negative. So it is even number, but it may be positive or negative. Similarly here 105 into 2k, it is always even number, but if k is positive, then minus plus minus is minus, and if k is negative, then minus minus is plus, but ultimately this quantity is even, and plus 12. So if you consider even minus even or minus even plus even, so then again this quantity is even quantity, and this is 12. So finally it is even number. So even number is not equal to 105. So f of m is not 105 if m is of the form 2k. Now you go for case 2. Suppose m is equal to 2k plus 1. In that case f of m is equal to f of 2k plus 1. So again it is 2k plus 1 raised to 7 minus 105, 2k plus 1 plus 12. Now 2k plus 1 is odd, so odd raised to 7. So odd into odd 7 times, so it gives me odd, and it may be positive. 2k plus 1 may be positive or negative. If it is positive, then 2k plus 1 raised to 7 positive. If it is negative, then it is negative. Similarly here 2k plus 1 is odd, 105 is odd, so odd into odd is odd, and 2k plus 1 is positive, then this is negative, and if it is negative, then it is positive, odd, and plus 12. So odd plus or minus odd is even, and 12. So finally it is even, so it is not equal to 105. So here what we have proved, if m is any integer, then it is odd or even. In both the case f of m is never 105. And there is one more observation. F of m, let me put in the, so from here we can conclude that this says that for m belongs to z, f of m is equal to even. It is not odd, so it is not, definitely not 105, but more than that it will be not an any odd number, it is always even. So option B is wrong. So option B is what? Wrong. Now in option C they say that there exists an integer m such that f of m is equal to 2. See, so f of m is even, so chances are that f of m is 2. So let us check for which value of m f of m is 2, or such m does not exist. So we have to verify it. So for that, so let us go for option C. So we have fx is equal to x raised to 7 minus 105x plus 12. Now f of m is equal to 2. It means what? It means m raised to 7 minus 105 m plus 12 is equal to 2. If and only if m raised to 7 minus 105 m plus 10 is equal to 0. It means what? Let me say it is gm is equal to 0, where gm is equal to x raised to 7 minus 105 x plus 10. So means gm is 0, where gm is gx, I have to write it is g x is this one. So now this gx is equal to x raised to 7 minus 105 x plus 10. It is a polynomial over q. Now 5 divides 10, 5 divides minus 105, and 5 does not divide 1, and 5 square does not divide 10. So therefore gx is 5 Eisenstein. So therefore gx is irreducible over q, and plus gx is monic, and gx is monic polynomial. So therefore gx is irreducible over z also. So therefore what we have? Therefore g of m is not equal to 0 for all m belongs to z. Gx is irreducible over z, because degree of gx is what? Degree of gx is sorry, no need to go for the degree of gx, but it has no 0, it is irreducible over z. So therefore, and here we have proved gm is 2 only if gm is 0, and if gm is 0 then fm is 2. So f is 2, value of fx is 2 for some m, if and only if value of g is 0 for some m, but gm is never 0 for all m. So therefore f of m is not equal to 2 for all m belongs to z. So fm is never 2. And in option C, they says that in option C there exists an integer m such that fm is equal to 2. So option C is wrong. And now option D. Option D says that fm is not a prime number for any integer m. So yes, fm is not 2, and if you consider any prime other than 2, then it is odd. So fm is always even. So here let me put for option D here, fm, let me write at the last page. Now for option D, fm is always even and fm is not equal to 2. So therefore fm is never prime for all m belongs to z, because if you consider any prime other than 2, then it is always odd, and fm is always even. So fm is never odd prime. And about even prime is only 1, 2, and we have proved that fm is also not 2. So we can say here option D, fm is not a prime for any integer m, so that is correct. So option 7 is correct. Option D is correct. Sorry, here in option A, we get fx is irreducible over q, and option A says that fx is reducible over q, so it should be incorrect. Now problem number 8. Which of the following polynomials are irreducible in Z? Which of the following polynomials are irreducible in Z? So here option A is x raised to 4 plus 10x plus 5, 4 degree polynomial, or in option B 3 degree, in option C 4 degree, and option D 3 degree polynomial, and all the polynomials are monic polynomials. So let us go one by one, and they are asking over irreducibility over Z. So all the polynomials are monic, so irreducibility over Z or Q are equivalent. So let me go for option A. Here fx is equal to x raised to 4 plus 10x plus 5, and this is what? This is 5 Eisenstein, because 5 divides 5, 5 divides 10, 5 does not divide 1, and 5 square does not divide 5. So it is 5 Eisenstein. So therefore fx is irreducible over q. So therefore fx is irreducible over Z, because fx is monic. So therefore, and we are in question, we are looking for irreducible over Z. We are, which of the following polynomials are irreducible in Zx. So option first, option A is correct, it is irreducible. Now let us go for option B. So say gx is equal to x cube minus 2x plus 1. Now g of, you may consider it is over qx. Now by inspection, g of 1 is what? 1 minus 2 plus 1, it is 0. Is equal to 0. So therefore gx has a 0 in q, and degree of gx is equal to 3. So we know that result, if degree of polynomial is 2 or 3 and it has a 0 in f, then it is reducible over f. So therefore gx is reducible over q. So therefore gx is reducible over Z, as fx gx is monic polynomial. And in option B, so this polynomial B is reducible, and we are interested in irreducible, so option B is wrong. Now you go for the option C, x raised to 4 plus x square plus 1. So let you say hx is x raised to 4 plus x square plus 1. So now consider this is over zx. See here degree of hx is 4, so we can't use the result that fx has a 0 in f if and only if it is reducible, because degree of hx is not 2 or not 3. But it is easy to see that you observe these two factors, x square plus x plus 1 and x square minus x plus 1. So you look at the product of these two factors, then it will be what? X raised to 4 minus x cube plus x square plus x cube minus x square plus x square minus x plus 1. So it gives me what? X cube cancel, x cube cancel, x square cancel, x cancel. So we left with x raised to 4 plus x square plus 1, and this is what? Hx. So Hx is a product of two quadratic polynomial and both are in Zx. So therefore Hx is reducible over Z. So therefore option C is wrong, because we are interested in irreducible polynomials. Now option D. Set Tx is equal to x cube plus x plus 1. So it is over Qx. So it is a polynomial of degree 3. So suppose Tx is reducible over Q. So let alpha is equal to r by s, with r and GCD of r and s is 1, be a root of Tx in Q. So by rational root theorem, r divides 1 and s divides 1. R divides the constant term and s divides the leading coefficient. So it gives r is equal to plus or minus 1 and s is equal to plus or minus 1. So alpha is equal to r by s is equal to 1 or minus 1, and by manual calculation f of 1 will be 3 not equal to 0, and f of minus 1 is minus 1 plus 1 plus minus 1 plus 1 is equal to minus 1, which is not equal to 0. So therefore f of x has no 0 in Q, and degree of fx is equal to 3. So therefore fx is sorry, not f, it is t. So let me correct at every place. It is t of 1, t of minus 1, t of t, and here also Tx is irreducible over Q. So therefore Tx is irreducible over Z. So our option D is correct. Now problem number 9. Problem number 9, it was asked in June 16 in part C. Fx is in Zx be a polynomial of degree greater than or equal to 2. Pick each correct statement from below. Fx is irreducible in Zx, then it is irreducible in Qx. And Fx is irreducible in Qx, then it is irreducible in Zx. So this is a standard theorem, standard result, and you notice that Fx belongs to Zx be a polynomial and degree of is greater than or equal to 2. So we know the result. And the result is what? If Fx belongs to Zx, then Fx is reducible over Q implies Fx is reducible over Z. Converse is not true. Converse is not true. Converse is true if Zx is monic, and here it is not given that Fx is monic. Right. So Fx is reducible over Q implies it is reducible over Z, and converse is not true. And the contrapositive of this one is what? Fx is irreducible over Z implies Fx is irreducible over Q. So this says that therefore option A is correct. So option A is correct. Now about option B, Fx is irreducible in Q, then it is so for that option B we have this, you take Fx is equal to 2x square plus 4 belongs to Zx, then it is what? 2 into x square plus 2. So it is what? Therefore Fx is reducible over Z, but Fx is irreducible over Q. So Fx is irreducible over Q, but it is not irreducible over Z. So option B is wrong. Now option C says that Fx is irreducible in Zx, then for all prime P the reduction f bar x of Fx modulo P is irreducible in Zpx. So here you may consider Zpx is what? First of all, let me go for option C. First of all, Fpx, it is same as Zpx, filled with P elements. Fp means filled with P elements. So you take Fx, let me change F, you consider say Gx, consider Gx is equal to x raised to 4 plus 1, so it is in Zx, degree of Gx is 4, which is greater than or equal to 2, and Gx is irreducible over Z. So it is easy to see that Gx is a polynomial of degree greater than or equal to 2 and it is irreducible over Z. Now let P be any prime. Then you consider G bar x belongs to Zpx. Then G bar x will be what? You reduce the coefficient of G by modulo P, and here in the G, So coefficients are 1. So g bar x is also x raised to 4 plus 1. It is belongs to zpx for every prime p. So we know that this is what? This is it is reducible over zp for all prime p. This is a well known result. I am writing here due to this is what? Well known result. It is reducible for over p for every prime p. So for option D we have fx is irreducible over zx, but it is reducible over option C we have an irreducible over zx, but f bar x is reducible for all prime p over fp. So option C is wrong. And now option D says that fx is irreducible in zx, then it is irreducible in rx. So it is very simple. You look at for option D, you take fx is equal to x square minus 2 belongs to zx, then this is what? Irreducible over z, but you can factorize it is x minus root 2 and x plus root 2. So this is what? Irreducible over z, but reducible over r. So we can say here option D, fx is irreducible in zx, then is irreducible in rx. So it is wrong. Now problem number 10. Which of the following is an irreducible factor of x raised to 12 minus 1 over q? So we are interested in the irreducible factor of x raised to 12 minus 1 over q among options A, B, C and D. So there is a, let me give one result first. So there is a result. Highest highest degree of irreducible factor of x raised to factor of fx is equal to x raised to n minus 1 is equal to phi of n, where phi is Euler's phi function. So if you are interested to find the irreducible factor, of a polynomial of the form x raised to n minus 1, then this result says me the degree of highest irreducible factor, highest degree of irreducible factor is phi n. Means a factor or a polynomial having degree greater than phi n, and if it is a factor of x raised to n minus 1 and x raised to n minus 1, then it must be reducible. It is not irreducible. So to have irreducible factor of x raised to n minus 1, the degree of that factor must be less than or equal to phi n. So if I use this result, then here my fx is equal to x raised to 12 minus 1. So n is equal to 12. So therefore phi of n is equal to phi of 12, and phi of 12 is 4. So therefore irreducible factor of x raised to 12 minus 1 has degree less than or equal to 4. So by this, in option A and D, the polynomial has degree 8 and 5, and it is greater than 4. They are not less than or equal to 4. Now I don't know whether it is a factor or not of x raised to 12 minus 1, and I will not check it. If it is a factor, then it must be reducible by this result. So therefore option A is wrong, and option D is also wrong. So option A and D are wrong. Now option B, x raised to 4 plus 1. So let me check whether x raised to 4 plus 1 is a factor or not. So let me consider by manual calculation. So for option B, let me consider x raised to 12 minus 1 divided by x raised to 4 plus 1. So it is what, x raised to 8. So x raised to 12 plus x raised to 8, and here I get minus, so minus x raised to 8 minus 1 minus x raised to 4. So it is minus x raised to 8 minus x raised to 4 plus. So it gives me x raised to 4 minus 1, now plus 1. So x raised to 4 plus 1 minus, so it is minus 2, which is not equal to 0. So remainder is not 0. So therefore x raised to 4 plus 1 is not a factor of x raised to 12 minus 1. So therefore option B is wrong. So option B is wrong, and hence in part B only one option is correct. So option C is automatically correct, and if it is in part C, then also we have C is correct. So now I will not check for option C. So definitely it will be a factor of x raised to 12 minus 1, and its degree is also 4, and it should be less than or equal to 4. So C is the answer. So here we have seen 10 problems based on reducibility and irreducibility, and there are some more problems, but we will see in the next lecture due to the length of the video. So we stop here, and the remaining problems we will see in the next video. Thank you.